Okay, so does this work? Okay, so does this work? Okay, it seems to be working. Very nice. Okay, so this time today we're gonna have a very short stream because I have a lot of school assignments to do. It's currently 7:30 a.m., which is kind of early in the morning, and I actually woke up at 5 a.m. In the morning. So yeah, this is gonna be probably 1 hour long stream where we carry on with our description of this GPT-2 module here, and we did the forward method for the multi-head attention class before. So now we're gonna do the feed forward function. And before I even start with this, I will just want to know a more or a better definition, I guess. So, what is a feed forward function? Forward. And let's actually don't search because that is some old stuff. Let's ask an AI, and I want to use Mistral AI just for my own preferences. So what is a feed-forward? Okay, so a feed-forward network is a type of artificial network where connections between the nodes do not form a cycle. It is one of the simplest, most commonly used types of neural networks. Here's a detailed description. Now I'm actually gonna post my code here just so it can explain it as well. Your implementation is of a simple feed-forward network uses PyTorch, almost correct, but there are a few issues. Okay, so important statement. You need to import the necessary I have already done that, obviously. Dropout parameter. The dropout parameter is used in the NN.dropout layer, but is not defined in the initial function or definition. You should either pass it as an argument to the init method or define a default value. Forward method. The forward method should take an additional parameter self to refer to the instance of the class. Why have I not done that? So we use self here. We use self here as well. So actually I've done that. Either way. Yeah. Okay, so anyways. The process. Forward propagation. The input data is passed through the network layer by layer. Each node in a layer receives inputs from the nodes in the previous layer and performs a weighted sum of these inputs. Add a bias term and then applies an activation function to produce an output. The activation function should be a ReLU if I'm not... Exactly, yeah, it's a ReLU. This output is then passed to the node in the next layer. Okay, so it's just to add another layer of logic, basically. Activation function. This is a function applied to the weighted sum of inputs to introduce a non-linearity into the module or model. Common activation functions include sigmoid function, the tanh function, and the ReLU rectified linear unit function, weights and biases. So each connection between nodes has associated weight, which determines the strength of the connection. Each node also has a bias term, which is added to the weight sum of inputs before applying the activation function. Okay. Loss function during training the network's output is compared to the actual target values using a loss function. Common loss functions include mean squared error for regression tasks and cross-entropy loss for classification tasks. Backpropagation. The error is propagated backward through the network using the chain rule of calculus. Interesting. That is a very simple mathematical equation, actually. This process involves calculating the gradient of the loss function with respect to each weight and base bias in the network. So basically, the loss values go backwards in the module, and then it will come out as a gradient. And I think a gradient is essentially a vector, if I'm not mistaken. So it will be a list of values. Optimization. The weights and biases are updated using optimization algorithms such as gradient descent to minimize the loss function. This process is repeated for multiple epochs until the network converges to a solution. Okay, that is not super hard to, or it actually is quite hard to understand, but if you know the math behind it, then it becomes more clear or a visual picture in your head. So feed-forward neural networks are used in a I cannot of many applications, including image and speech recognition, neural language processing, which we do now, predictive analytics. Okay. Feed-forward neural networks are simply to implement and understand. Efficiency, they can be trained efficiently using back propagation and gradient descent. Versatility, they can apply to a wide range of problems from regression to classification. Okay. Yes, so that is not too complex, to be honest. So basically what we do, we initialize the neural network and we create a sequence of layers, which is the linear layer with these parameters here, and the ReLU, which is the activation function, and another linear linear layer, which, by the way, I think the reason why we are multiplied by 4 here is to get the right dimensions. And then we have a dropout function. Now, here's something interesting that I didn't even know about, but I talked to a teacher at my university about the dropout function that PyTorch has, and it is actually quite bad. The dropout function is not optimized at all. So it might be wise to implement your own dropout function. And I will actually look into that more. And then we just return the self.net.x, or x, and x is, I guess, the value. Okay, so it's not the most complicated function. But yeah. So let's just add, we cannot add comments if I'm not mistaken, so we're gonna skip the comment here. And I don't have a compiler for Python or LaTeX. That is fine. So import that. And I also might want to create a subsection here. Which is gonna called the feed forward function or definition. Right. So let's create this list of description here. We don't need to have the example usage, but we need this here. Feed forward, this is the name of the class that defines our feed forward neural network. And then we just have some back information about the subclass. So the NNN.module, this is the base class for all neural networks in PyTorch. By inheriting from NNN.module, we get access to various functionalities like parameter management and moving the model to different devices, which is CPU/GPU. Pretty straightforward. And then we can. By the way, this should actually be a subsection. It makes more sense. And then we basically do subsections for the different definitions inside of the class. And that's wrong. And then we're gonna use this code block here. Copy this here. That should be the code. That is actually not the code. Never mind. And this should be like this actually. So we're gonna copy this definition here and paste it here. Yeah. So the init class. This is the constructor method that initializes the class. Yep. The embed parameter. This is the size of the input embedding. It determines the number of input features. That's true. Dropout. This is a dropout rate, which is used to prevent overfitting by randomly setting a fraction of input units to a 0 at each input during training. The default value is 0.1. Then we have superfeed, which is not what I wanted. It should just be this should actually be this one here. So this calls a constructor of parent class and an end module to initialize it, basically. And then we have, let's see. Yeah. So self.net, this defines a sequential container that will hold the layers of the neural networks. Yeah, that's quite self-explanatory. Oops. And obviously this is wrong because I have underscores here. So we have to do backslash here just to define them. This is a LaTeX thing, it's not a Python thing. Just to make sure you guys understand that. And we also have another error somewhere. Well, I wonder where. Ah, here. Nice. And then we have the different layers in the sequence, basically. And we have underscore here, so we have to fix that, but either way. And we also have underscore here. And we have another underscore. Oh my god, there's so freaking many underscores. Okay. So this is a fully connected linear layer that takes n embed input features and outputs, which is multiplied by 4. The reason why we multiply by 4 here is because this layer will go through this activation function and then go to this layer. So the output from this layer, to make you guys understand this layer here will have, just for simplicity, say 4 outputs, right? But it has 1 input, right? Let's say this is 1, and this variable is 1, and this is 1, right? So this linear layer will have 1 input feature, but 4 output features. Then it will go through an activation layer or activation function, which then will go to this linear layer And we need to have 4 input features because this has 4 output features. And then we will actually just get 1 output feature of that. So it's technically, let's see. Can I explain this in a more visual manner? Notepad. Let's see if I can actually write something. Whiteboard. Maybe. Let's see if I can write something here. Okay, so we have a pencil. So let's create these layers. So this is 1 neuron. This is 4 neurons, or 2 neurons, 3 neurons. Oh, okay. And this is, let's see. Can I erase these? Yeah. And let's create a better circle here. Okay, so we connect here. Boom. Okay, so we have about these 4 neurons. Let's say we have 4 neurons, right? Now every so this is a layer basically. This whole thing here is a layer. Layer. Okay, this is super bad writing. Oh my god. Anyways, so this layer will essentially have 1 input feature. So this is just 1 input feature, right? And then we have a ReLU. We call it rel or ReLU, like that. And this will have 4 output features, right? Like this. And then we have another linear layer. Let's see if I can write this decently. With 4 neurons inside of it as well. Oh, that didn't work. Now, what this activation function will do is essentially it will just non-linearize the linear layer that we just added here, but it still will get us 4 outputs. So we need to have a 4 input feature in the next layer to actually work with this. And then it will just have 1 output feature. So this is basically how the feed-forward neural network looks like. And all of these has a biases and weights and so on. But this is basically, and this is also a layer. Oh my god. And what basically I can actually layer, come on. Nice. Okay, so this is basically how the structure actually looks like here. So we create a linear layer with 1. Okay, so technically it's not in this structure. Technically it is a much larger structure, but just to keep it for simplicity, we just go with the basics, right? So this will create, this code here will create this layer here, and this ReLU is an activation function between these layers, which is this ReLU here. And this layer here is essentially this layer, which is almost identical to this layer, but the differences is that the input features here on this layer is 1. We can see that here, this is the input feature. And the input features on this layer is 4. So this is 1. This is 4. And the output feature on this layer is 4. And this is 1. And this is output layer for layer number 2, which is 1. So this is basically how you can describe it in a more simple manner. So this is basically how do I even move this table? Can I move this? Nope. Ah, never mind. Doesn't matter. So this is basically how you can look at it. And weights, I'm not gonna paint out the weights and biases because then we get into a more mathematical perspective and not a graphical one or a visualized one. But I highly recommend you guys understand what weights and biases is. And then you will be introduced to deep learning and the more the mathematical aspect of AI basically. So this is the feed forward function. I can write it here. Feed forward. Yeah, my writing is super bad. Whatever. So this is the feed forward neural network, basically, in a more simplified way, basically. So let's go back to the AI. So we have described the linear that is fully connected, linear layer that takes this, say for example this is 1, and the output features is 4 basically. It's technically not that, because if we look at the code, we have set the embed parameter to be 384, which means that we have 384 neurons in this layer and 384 neurons in this layer, and the output features are 4 times 384, which is basically, if we calculate that, that is equal to 1,536 output features in that. So it's gonna be 1,536, I think it was, yeah, strings here to the value. So the network is more complex than I did write out here, but it's the same theory behind it. Okay, now we have explained that. We can carry on with our own description here. So we have an value from value activation function here. This applies the value rectified linear unit activation function to introduce non-linearity. And that we talked about that. We also have another layer, linear layer, with a lot of backs underscores. Oops. That's fine. Nope. Oh, we have one here as well. Okay, nice. So we have the n-ant linear with this another fully connected layer that takes 4 n input features and output 1 outputs embed features, right? And then we have the dropout. So this applies the dropout with specified rate to prevent overfitting. Right. Now we have another subsection. Nice. And then we can create a table of contents. So the forward, the method defines the forward pass of the neural network. The X is the input tensor to the network, and self.nextX This passes the input to tensor X through the sequential container self.net, which applies the defined layer order. So basically what the forward function does is essentially just to return the values that we get from the neural network that we pass the matrix through. Yeah. And now we're come to the, I think it is the block function, actually. And of course, we have another comment here, which we don't want to have. Yeah, that seems to be all right. It seems like the AI actually just don't want to describe the multi-head attention, but I think we did that up here. So yeah, we probably don't. This code defines a multi-head attention class that implements a multi-head attention mechanism for transform module. The class inherits from nn.module, which is the base class for all neural networks modules in PyTorch. Let's break down the code step by step. Okay, so it obviously crashed. I'm not even surprised. But anyways. So we have the class definition. Let's start with that. Oops. So the block is the name of the class that defines a transformer block. Okay. I actually have to check more to that. And obviously the NN module is the base class for all neural networks in modules in PyTorch. Then we have the initializer. That's the third. Initialization method. This. So the init, this is a constructor, obviously, the method that initializes the class. The embed. This is an embedding dimension which determines the size of the input features. Then the n head. This is number of attention heads, which we defined as a super parameter. The super init, and obviously this is not wrong because there are a lot of underscores. Now we have the super.init function. This calls a constructor of a parent class and another module to initialize it. So it initializes our own init function or the class that we defined. The head size, this calculates, by the way, this is an underscore here. The head size, this calculates the size of each attention head by dividing the embeddings dimension by the number of heads. This is important because otherwise we will get the wrong dimensions. So it's good to remember to having the right dimensions. Then we have self.sa. This initializes the multi-head attention mechanism. Is assumed to be a class that implements multi-head attention, self-attention. Yep. And I think we don't even need that. Then we have the feed-forward function. So this initializes the feed-forward neural network. Feed-forward is assumed to be a class that implements a feed-forward neural network with a linear layer followed by non-linearity, which is why we used a combination of linear layers and ReLUs, which is basically this picture here. Oh my god, how do you even zoom out here? Either way. And then we have this here. So the self-linear 1 and self-linear 2, these initialize the layer normalization layers, which are used to normalize the inputs to the subsequent layers. Why is this important? Well, that's because AIs cannot compute with values smaller than -1 or greater than 1. So we have to normalize every value from a specific ratio to actually be able to compute with these values, because when we convert words into values, the values is greater than 1 or less than 1. So we have to normalize the values to make sure that the neural network can actually compute. For example, with this network here and all other neural networks cannot use values that is lesser than -1 or greater than 1. And that is because of probability theory. So now we have the feed forward, or the forward method. So the forward method, this method defines the forward pass of the transform block. Okay. X, this is the input tensor to the block. Pretty straightforward. And then Y is equal to is equal to, this applies the multi-head self-attention mechanism to the input X and stores the result in Y. So basically, what we do here is in Y, we apply the self-multi-head attention layer to X and then get a result which we store in Y. Now, if you guys haven't watched the other live streams I've done, what multi-head attention does is essentially adding a vector to every word that basically contains information about the connection between another word. So we can basically connect words by numerical values in a vector that is and that is attached to the current word that we are looking at. And the reason why we use multi-head attention and not single-head attention is because we can calculate these vectors in parallel, which increases the efficiency of the neural network a lot. I would still say that the neural network itself is inefficient because it's a very simple neural network, but it definitely enhances the neural network itself. So x.self linear 1 x plus y. This adds the original x input x to the output of the self-attention mechanism y, residential connection. This is where the connection. So y is basically the vectors and x is the input. So we add the vectors here to the input, basically. And then applies the layer normalization using self.ln1. Then we passes the normalized output through the feed-forward neural network and stores the result in y, which is this network here. So basically what we do is we take a matrix of input, add it to the multi-head attention function to create vectors, and then add the input and the vectors together, and then if we pass it forward to the feed-forward mechanism that basically non-linearize and calculate the function, the predicting function that the AI uses. And then we do that again. And then we return x. And I obviously didn't put the code here. That's my bad. And I honestly think I will stop here because this whole function here is super long. So I will actually just wait with that because that is gonna take a real long time to explain. This is basically the main part of the whole training.py file. So I hope you guys enjoyed it. I know there is not a lot of people here at the moment, and that is understandable because it is super early in the morning. So I hope you guys enjoyed this video. I hope you guys learned something from it, and I will summarize all of these live streams with a video on my channel at the end. So yeah, I hope you guys enjoyed this, and thank you for watching.